Hi, in this video, we'll be continuing understanding more about joint probability distributions. Specifically, we'll talk now about what is the expectations and the concept of covariance. So for a single valued probability random variable, there is something known as the expectation, which is your weighted average, and likewise, there is also an expectations for continuous for two or more random variables using the joint PDF. And really, if you have a function that is related to x and y, then the expectation of this function occurring is you can just do lotus, which just means the law of the unconscious statistician, and really you're just keeping the PDF, the joint PDF, and this x that you have will now be replaced with gxy. So it is exactly like the same idea as you normally would do for a single valued one, but in this case now you have to integrate with respect to x and respect to y. So that's all for expectations really. The more important thing about when you have two or more random variable is really how are they related to one another, and how do we capture and measure this relatedness. And that's really what it means by covariance. And so the covariance of x and y is defined to be the expectation of e minus mu bracket y minus mu of y. And then if you are able to simplify this by expanding this and simplifying it, you actually get that the covariance of x and y is equals to the expectation of xy minus away the expectation of x times the expectation of y. And so the covariance of x comma x is actually equals to the variance of x, because now you replace this with x, it means you replace this with x and this with x. This is just ex squared minus the expectation of x whole thing squared, and that equals to the variance of x. So why do we study covariance? Well, it helps. We can also study this thing known as the correlation, which is just covariance over the standard deviation of x times the standard deviation of y. So it's just a standardized form, and so we can actually show that correlation is between -1 to 1. And really, when we say, so we'll just use this standardized form, and we can say that there's a positive correlation between two random variables when the correlation is closer to 1. So the closer it is to 1, the more positively correlated it is. So it's the measure of how linear these two random variables are related to one another. So this you can see as x increases, y increases, and so it goes along like the y equals to x line, and that's why it's known as positive correlation. And for the other case, when x increases, y decreases, and so it goes along the y equals to minus x line, and that's the negative correlation. And so negative correlation just means that this correlation is negative, and positive means it is greater than 0. And the closer it is to 1, or in the negative sense -1, meaning the larger the magnitude of this correlation factor, then the more linear the relation is between x and y. And so if you're scattered all over and there's no correlation, there's independence between x and y, so x don't affect how y is and y don't affect how x is, that means they're independent, then they will be uncorrelated, and we'll prove that later on. However, it is possible to still be dependent but uncorrelated. So x and y are not correlated, meaning they don't have a linear relation, but they're dependent in a following sense that it follows like y equals to x squared. So that's a dependent they are dependent. And really, the properties of covariance are very similar to that of variance, because the covariance is just equals to covariance of x comma x. And so when you add a constant to one side, it doesn't change the covariance. Just like how adding a constant to the variance doesn't change it. But if you multiply one of the random variables by a constant, then you can pull out the constant. And then we know that the covariance is symmetric, also same as variance. And really, the most important thing about covariance that it is bilinear, meaning it's linear in the first argument and linear in the second argument. And property 4 just shows how it's linear in the first argument, where if it's x plus y, then you can take out and become xz, covariance of xz plus the covariance of yz. And because it's symmetric, it's also linear in the second argument. And hence, the following result is one that more people apply usually, is that the covariance of x plus y comma z plus w is the covariance of xz plus the covariance of xw plus the covariance of yz plus the covariance of yw. And why is that so? It's because this can be written as covariance of x comma z plus w plus the covariance of y comma z plus w. And then you just expand this into the two terms here, and the one below is here and here. So these are the properties of covariance that you will find useful. And the last thing we would like to talk about is what I've said earlier, where we can now calculate the variance of x plus y more easily with the help of covariance. And so now we know that the variance of x plus y equals to the covariance of x plus y comma x plus y. And by using the bilinear property, we are able to simplify and expand it out into covariance xx plus covariance xy plus covariance yx plus covariance yy. And so this is just the covariance of x, and this is the covariance of y, as follows. And the covariance of xy is the same as the covariance of yx. So it's plus 2 times the covariance of xy. And you can generalize this to summing over a finite number of random variables, and it will just be the sum of all the variance plus 2 times the covariance of xi comma xj, where I is less than j. And so, like the graph earlier, where it is dependent on each other but uncorrelated, we can actually prove that if the random variables are independent, then they are also they will be uncorrelated. So the proof really follows because the expectation of EY equals to the expectation of X times the expectation of Y. And really that's because you know that the joint PDF can be separated into the marginal PDF times the marginal PDF of Y, also X times the marginal PDF of Y. And so this portion, the Y portion, you can collate them. And the X portion, not because they are not related to Y, now you can collate them as well. And really you just get the following by definition. And so because covariance is the expectation of xy minus x times ey, this is now 0. And if covariance is 0, correlation will be 0 as well. And so they are uncorrelated to one another if x and y are independent. However, we like to note that uncorrelated does not imply independent. For example, the case where y equals to x squared, it is very dependent because whatever the value of y is just squared version of whatever x is. But if you calculate the covariance, you will know that the covariance is 0, so it's uncorrelated. And you can also show that the covariance being a standardized form of the correlation being a standardized form of the covariance will just result it in between -1 and 1. And really, you're just using that the variance of x plus y is the following. And since you know that the variance of x plus y is between 0 to 2 plus 2p, it leads to p being greater or equals to -1. And likewise, you can consider the variance of x minus y to get the upper bound now. And so really that's about it for understanding covariance between two random variables. So I hope you have enjoyed this time in learning about joint distributions. And really the idea is that it helps us simplify our ability. It can help us simplify our variance, because now variance can be written as covariance. So you can check out more examples in the textbook, and I urge you to practice them. And in the next video, we'll be talking about moments, which is a very important concept because moments define a distribution as well. And so I'll catch you in the next video. Thank you for listening and have a great time. Bye.